Hi everyone. In this video, I'll be presenting my research paper on monocular depth estimation using multi-scale neural network and feature fusion. In this work, we propose a novel network for estimating the depth from single camera images. We trained and tested our network on three kind of data sets. One is the Make 3D data set, the other is NYU depth, and the third is Kitty data set. We use standard evaluation metrics using RMSE log and SI log loss for evaluating a network. Our network is able to perform on par with the previous state of the art uh, networks while it's still running at a good enough FPS, thus making it work for real time applications. So, as a brief overview, like our network here is an end-to-end trainable network, thus making it integrable for real-time applications, especially which is important in the autonomous driving community. And it is a kind of a plug-and-play, so it can be easily integrated into other kind of networks also. Our network is lightweight, so in uh, and our network at the same time is like performing better than the most of the previous state of the art using three different data sets. So as an overview, like we first perform data augmentation to increase the size of the data set. Some of the operations which are performed here is scaling, rotation, color jitter, color normalization, and flips. Briefly going over the network, like we have feed and input to a network, which is propagated to like a convolutional block, and then which is then propagated to a backbone made up of ResNet architecture, residual networks. We employ multi-scale concept here with different kind of convolutions like 1 by 1, 3 by 3, 5 by 5, and 7 by 7 convolution. We use concat operator to merge the features from all the four individual blocks. Similarly, then we feed it to our next set of convolutional layers in parallel. Here we employ dilated convolutions here. So in one part, like we haven't used any dilation. In the second, we use a dilation value of 2. In third, we use dilation value of 4. And then we further concat all the individual features and thus producing the final output, which is the estimation of depth. So here we use concept of multi-scale fusion, that is extracting features at various scales using a different convolution scales that is made up of 1 by 1, 3 by 3, and 5 by 5, and 7 by 7 convolution, and then merging all the individual features using a fusion operator. The loss function we have used is the commonly used like L1 loss, which is basically the difference of the absolute depth values. We also use SSIM loss here, which is defined using this equation here. We have used multinomial logistic loss here. So this is something which is like novel, although the first two terms of the loss function have been borrowed by previous papers. So this is something which we have incorporated here. And unlike in the fourth like equation, we summed up all the three individual loss functions with some alpha, beta, and gamma parameter values, which are basically constants here. As for evaluation metric, like we use RMSE as well as the RMSE log, which is defined using these two equations. We do use like SI log metric also, and we also use average relative error as well as the squared relative error, which is defined using these equations here. So these are some of the like, details of the previous evaluation metrics. And at last, like we also use mean relative error as well as the mean logarithmic error. Uh, as of implementation details, like we have provided them. So going over the results, like we trained and tested our network and benchmarked it against the previous state of the art. So our network does perform better than most of the previous state of the art. Although the results are old right now, so in the past like 1 year, definitely other networks do perform better than us. But still, like we are performing like on par with most of the previous state of the art using a bunch of evaluation metrics. So this is the the quantitative results on NYU depth data set. This is like the qualitative results on NYU depth, and similarly, like we also show the qualitative results on the kitty data set. This is like the qualitative on the kitty data set, the predictions. So here the first image here depicts the input image. The second is the ground truth depth map. The third is the predicted depth map. So color indicates here the distance of the an object. Uh, so here red color denotes that the object is very far, while the blue here denotes the object is near. And similarly, we present the quantitative results benchmarking our network on previous state of the art on Make 3D dataset. So here, uh, so these are the evaluation metrics like which we used. So all these metrics, the lesser, the better the results are. As of ablation studies, like we played with using no dilation as well as using dilation. And similarly, we played with using concat for merging the features, using a bunch of different evaluation metrics. So this ablation study is presented here in table 4. So finally, as a conclusion, like we propose a novel network for monocular depth estimation. Like we employ multi-scale fusion uh, and like merging the individual features, and so our network is able to outperform most of the previous state of the art using three different data sets on a bunch of evaluation metrics. In the future, we would like to use this concept of multi-scale uh, networks for tackling other kind of problems. I think this could be a possible research problem that could help other kind of uh, task in autonomous driving community, like maybe semantic segmentation or a bunch of other stuff. So yeah, thank you for listening.